it won't go to current slide. Ah, hit it too soon. This is from a Ms. Christina, Dr. Christina N. Mora. She's one of the newest cohort of merit scholars, whatever those are, at UAB. She came across this one-week summer opportunity for college students interested in biopharma. That's biology, pharmacology, pharmacology company, manufacturing careers, biopharma manufacturing careers. I thought one of your students might be interested in applying. The students are paid $1,000 for a one-week visit to a biopharma manufacturing plant. Travel expenses are covered, and the application deadline is sometime in January. So if you or anyone else you know might be interested in that, I have a link to a website that you can go to. So I found that really interesting, especially how much they pay. $1,000 for 1 week, and they pay your travel. So they're really looking for people, I guess. Okay. All right. Any questions on anything we've covered so far? Okay. Now, where we left off last time, we're just about to get to what we've done in Cal 3, okay, or one part of what we've done. We've been talking about different solutions of differential equations. Primarily interested in linearly independent functions, or more to the point, linearly independent solutions of a linear differential equation. All those we could always appeal directly to definition 4.1.1, which was back on the previous page, and those really nebulous definitions. If all the C's are 0, it's linearly independent. If at least one of them's not 0, it's linearly dependent. Not a very easy thing to do, especially for a large group. Okay? It turns out the question of whether a set of n solutions, y sub 1, y sub 2, y sub 3, up to y sub n, of a homogeneous or homogeneous linear nth order differential equation is linearly independent can be settled somewhat mechanically by a determinant. Now, I don't know if you remember, determinants also tell whether systems of equations are linearly independent. You may not have had linear algebra yet, but they can tell you that as well. Okay? So let's suppose that we have n functions. Let me get my pen set up. F sub 1. Do they put of x here? Yeah, they do. Okay. More to the right. F sub 2 of x. F sub 3 of x. Dot, dot, dot. All the way up to and including f sub n of x. There you have n functions. Each of those functions possesses at least n minus 1 derivatives. Whoa. So the more functions you have, the more derivatives you have to have. Okay? And each of them must possess or possesses at least n minus 1 derivatives. Okay? So what you do then is take n minus 1 derivatives of them. So you take f sub 1 prime of x, f sub 2 prime of x, f sub 3 prime of x, dot, 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 all the way up to f sub n prime of x. Okay? You take f sub 1 double prime of x, f sub 1 double prime, or f sub 2 double prime of x, f sub 3 double prime of x, dot, 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 up to f sub n double prime of x. You've got a lot of differentiation to do here. Okay, now some of these could turn out to be 0, and that's sort of okay too. Okay, and then finally we get dot, dot, dot down to f sub 1, the n minus first derivative of x. Alpha sub 2, the n minus first derivative of x. Alpha sub 3, the n minus first derivative of x. Dot, 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 up to alpha sub n and the n minus first derivative of f sub n. Oh, I thought I did. Sorry. I thought we all let me go, huh? I thought I hit the button when I came in. Well, either I didn't or I didn't notice that it didn't start blinking. So, I've got the recorder on, but I thought it was coming on when I was holding that sheet up in front of it, but wasn't paying attention to it. Okay. So, you have all these functions and all the derivatives. Okay? Now, what I'm going to do is take out my commas. Okay? This is almost cheating. It really is. Okay? I'm going to take out all the commas there. And now we just got arrays of numbers, or functions, and derivatives of functions. Oh, I didn't even put my commas in there. Oh! Took out my 1 rather than my comma. Okay, left off another comma. Okay. Now, y'all know what why am I going blank on this name? Determinants are. Just barely, okay. Well, we'll be doing them. This now, an array of numbers or functions or whatever are there, and a determinant tells you to do something very special with that array. Now, I didn't leave enough room, so I'm going to write this on the other side. This determinant is called the Wronskian of these functions, f1, f2, f3, dot, 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 up to and including f sub n. That's the Wronskian of that set of functions. Okay? Now, I guess I should spell it for you too. W-R-O-N-S-K-I-A-N, the Wronskian. Obviously named after Wronski, okay? His name was even worse than that. Named after the Polish philosopher and mathematician Józef Maria Horny Wronski, okay, or something like that. And believe it or not, he lived back in the 1778s, that's just 3 years after our country was born, to 1853, just a few years before it almost fell apart. Okay, so now here's the theorem that goes along with that. Let, this is theorem 4.1.3, let y1, y2, y3, dot, 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 up to and including y sub n, be n solutions of the homogeneous or homogeneous linear differential equation on an interval I. Okay, now that differential equation is the one we've been talking about all along. I didn't write it all down. Okay, these are all solutions. Okay, they've got to be solutions to the differential equation. Now, what we don't know is whether they're linearly independent or not. Okay, if they're dependent on one another, well, they're not a complete set, you might say. We'll get to that later. So that's what we're given. Then the set of solutions right there is linearly independent okay, on I. Now here's, ooh, goodness, that's ugly. Okay. I was doing that earlier. I wondered what in the world it was. The pen's dragging. That's why those strange marks were there. I didn't figure out why, but now I saw it. Okay. Now this is if and only if. This is a real quick and dirty symbol for that. If and only if. One's true, but the other, it has to be true in both directions. If the Wronskian W of those functions, y1, y2, y3, dot, 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 up to and including y sub n, okay, is not equal to 0, that's supposed to be a not equal sign, for every x in the interval. Okay, that's a lot of shorthand. Now, we'll do some of these. We're going to keep it small. We're not going up to big numbers of n. Just doing a determinant of a large number of n, that's tough. But then when you have to do all those derivatives to get them in there, that takes a long time. So we'll do a little bit smaller ones. Okay. Now, from this theorem says when all those, see, why in the world they call them F's up here and Y's here? It doesn't matter. Y is equal, Y1 is F1, Y2 is F2, all that. Okay, it follows from this that when all these Y's are in solutions of your differential equation on the interval, the Wronskian is either identically 0 or never 0. I mean, it's either 0 or it's not 0. That's it, okay? Thus, if we can show that the Wronskian is not equal to 0 for some x of 0, then the solutions are linearly independent on I, the interval I. For example, this is going to be a real simple 2 by 2. Well, sort of simple 2 by 2. Here's y1. Not all that simple. Sort of brings you back to test 1, doesn't it? Cosine of 2 log x, not nearly as bad as that was, over x cubed. What a nice solution. Here's y2. Sine of 2 log x over x cubed. Okay? Those two functions I think that's supposed to be R solutions. They say, for example, the functions blah blah and solutions of differential equation blah on the interval. That's not a complete sentence. Must be, that should be an R there, not an N. Okay? But these are supposed to be solutions of this differential equation, x squared y double prime plus 7xy prime plus 13y is equal to 0. Now, I can almost guarantee you these two functions are going to have just as many derivatives as you care to have. But how many do we need to take here? Second? because n minus 1 derivatives. And this is only 2 second order linear differential equations, so you only need 1 derivative. Thank you very much. So let's do, I wish I hadn't written it there. Okay. However, knowing the studious, cynical people that you are, you probably want me to guarantee that is a solution, don't you? You want me to verify that, don't you? I knew you did, so we might need to take 2. Are you going to take their word for it?
I mean, I can, but I'm not going to do it.
Okay. Let's do y1 prime. Okay? What would it be? Ooh, boy. What rule do you need? You're going to need a couple of them. What's that?
First, we got to take the derivative of the 2 natural logs of x.
Okay. That's what rule are you using? Before that?
Do you want to do the quotient or do you want to
Can you do it without the, oh, you mean you ought to write that as x to the minus 3?
We can do that too.
Okay, which way you want to do it? Either way is fine with me.
I do the quotient.
Okay, it doesn't matter. How does quotient rule go?
We got x3, yeah.
Okay, low d high, so low is x cubed. Now derivative of that. And what's derivative of cosine?
Sine.
Minus a sine
Yeah.
of 2 log x. Now chain rule. Oh, I thought you just said it before. Derivative of the inside of that parentheses. Two over x. You see that? Okay. That's just the first part now. Okay. But I do know that that x will wipe out one of those, leaving only x squared. Okay? That's the low d high. Now you do a minus high d low, which is cosine 2 log n x, ln log n, I don't know what I'm saying, times derivative of the denominator, which is 3x squared. Okay, I'm not allowed myself enough room. All that's over what? X to the 6th. Low. X, denominator squared. Well, I can simplify that a little bit. I'm going to pull out my minus sign. Okay? And I know that 2 of these, bringing this down to 4, will wipe out those. Okay? And what I think I have now is 2 sine 2 log x. I don't know whether I'll leave the minus signs with it or separate. I think I'll pull the minus sign out, make it plus 3 cosine 2 log x. Now you tell me if I did that right. Over x to the 4th. I think so. Okay. I'm beginning to think, let's just take the word for it. Okay. What you say? Huh? Yeah, but the thing is we had to get a y prime anyway for the Wronskian. So we're not, that wasn't wasted effort. Okay. So you want to continue? Yeah, I can tell you do, y'all. Gluttons for punishment. Okay. Let's do our y 1 double prime. All right. What is that going to be? Yeah. Okay, minus x to the fourth Agreed? That's the first part.
We got a 4 over x, don't we?
Oh, over x. Yeah, you got it. I'm sorry. Wait a minute. Yeah, well, I put the 2 from that here, and this is over x. Yeah, you're right. Okay. I did the 2 with the other 2. Okay. Over x. All right.
We got a minus.
Okay, and yeah, this will be a minus inside the parentheses now.
6 sine 2
Okay, I already did the 2, so, oh, right, 2 log x
1 over x.
down 1 over x. Okay, that's just the first part. Minus, now let's see, this is in front of all of it. So let's continue down here with a minus.
That first thing at the top.
2 sine 2 log x plus 3 cosine 2 log x 4x cubed, right? Okay. All of that over, I'm only going to write it once, x to the 8th. They're both, well, I'll write it down here too. And see, we still have to do y2 both ways. Y'all really want to do this? Okay. All right. Now, all that's inside that. Now, this, I'm going to delete this parentheses. Oh, I thought I would. This parentheses here, because I don't think that was doing anything for me. Oh, yes, it was, because it's minus, no, it wasn't. Getting lost now. Yeah, I had to have that in there. Sorry. I needed that parentheses and close it out there. Okay, I didn't. Because that was minus that. Okay, is there any way to straighten this mess out? I keep encroaching. All right. Now, this x will wipe out one of those. So that gives me an x cubed here. And I think I did my parentheses in the wrong place. Now that I consider it. Well, that eraser doesn't come up. There it comes. I need to put that parentheses here, because that whole thing is times the d log. All right. Now, this x cubed and this x cubed will wipe out and make this x to the 5th. All right, so there's my y1 double prime. How about let's just show, and it works for y1, and then we'll say, because y2 is very similar, it's going to work for that too. Because the second derivative of a sine flips it around to the same thing, okay, as cosine. And all the over x cubed is going to be the same. So, let's try it that way. So this will be x squared times that will give us an x to the third in the denominator. Okay? Because the denominators here are x fifth. Here we multiply them by x squared. So that's going to pull that, make the denominator an x cubed. So let's just write our numerators down. Minus 4 cosine 2 ln x I'm going to distribute that. I hope I'm doing this right. The minus, if that is indeed in the right place, that will be a plus then 6 sine of 2 ln x. I already got rid of that. And then we'd have a minus. A minus, I hope, is going to be a plus 2 sine of 2 ln x. And then I think that's a minus, a minus, a minus times a minus, I think, is going to be a plus 3 cosine. And rather than writing all those arguments following the trig functions are the same, 2 ln x. So I'm just going to put parentheses from now on. Okay. That's that over x cubed. Okay. That's the first one. Plus 7. The x is going to cancel out your x fourths there, so that's going to give you x cubed, so I'm not going to write that down. But I'll put in parentheses here, and this is your y1 prime. And I think this line right here is it. And that's a minus in front of both of them. So what I think I'll do is change this to a minus and just multiply 7 by both of them. So that's, but it's not 7, it's a 2, so it's minus 14. I hope I'm doing this right. 14 sine of that minus 21 cosine of that. Okay. Then I've got to do a plus 13y. And your y was this first one, cosine of that. I started to write something there. I don't need to write anything there. That thing. Same argument. That hasn't changed any. And that's over 3. X cubed. So all these are over x cubed. So all we have to do to get this equal to 0 is get our numerators here. So I'm going to get rid of the over x cubed because they're all over x cubed. Okay. So let's see what we get. Hold your breath. Okay. Minus 4 cosine plus 3 cosine. That's minus 1 cosine. Minus 20. Oh! Minus. And only a plus 13 cosine. I think I did botch up something somewhere. And I think I see where it is too. No? Yeah. Whose idea was it to check this thing? Verify it. Oh, Bill's fault. Okay. Let's see if signs come out any better. Plus 6 plus 2 is 8. minus 14. It doesn't come out any better either, does it? Obviously, I've got some coefficients missing somewhere, or I multiplied them poorly or something.
I think that first.
Yeah, I've got so many pluses and minuses in there, and before and after parentheses.
On the first
Day of Christmas.
double problem, it should be 8 sine and 24 cosine, because not on the bottom.
Down here?
No, like right in the middle of the screen. Because we had to multiply by 4x cubed.
Yeah.
Right.
Oh. I may have left that one out.
That would have been it. I think that's going to be 8 sine.
Yeah, right here.
12 cosine.
That should have been in front of all these. Yeah, so that would have been an 8 here, and I don't think I got it. Yeah, I just got the 2. Forgot that. So that may be fairly easily rectified. Okay? Because it's just these two affected, I think. Signs may still be squirrely, but let's see. That would be an 8 here and a 12 here. Okay, now let's see how they go. Minus 4 cosine plus 12 cosine, that's plus 8. Minus 21 would be a minus 13 plus 13, ding, ding, ding. Okay, and let's see sines. That would be 6 and 8 is 14 minus 14. You got it. That's it. That 1, 4 right there I missed. Okay. So yeah, sure enough, that came out 0. All right, that wasn't a Wronskian at all.
Yeah, let's not do that.
Okay. So that was the unnecessary step. Okay. So, but we did show that it's equal to 0. For that one. We're not going to do the other one. I can't get this to erase. Alright. We don't need this anymore. We need the upper one, but not the lower one. We don't need the second derivative. But that was fun, wasn't it? In spite of making an error. Only could it have been like the first test question. No, that question on the first test is what I'm going to say. All right. We do need to do the first derivative of y2. y2 prime. Okay, and what would it be? X cubed. Going to have a minus, because, oh, no, not a minus, sorry. Okay, x cubed of cosine 2 log x times 2 over x, right? So this x is going to wipe out one of those. Minus sine 2, what am I writing this again? Times 3x squared over x to the 6, right? Okay, now the x squareds here and here will wipe out 2 of those, leaving us x to the 4th. Okay. And we get something very similar to what we had before, only different. And that would be 2 cosine of that thing minus 3 sine of that thing over x to the 4th. What's that?
It's just like the opposite.
Close, but not quite. Okay? Because you see, this is a minus and a minus, this is a plus and a minus. Okay? And these are sine, cosine, this is cosine, sine. So that part is sort of opposite. Yeah, there's similar, different, a little bit weird. Okay. So, what is our Wronskian? This is a 2 by 2. So we finally get to do a determinant. And what we put in the first row are your functions, y1 and y2, f1 and f2, whatever you want to call them. That's the determinant of cosine of this thing over x cubed and sine of this thing over x cubed. Your second row is your first derivatives, which is, I'm going to go back and put the signs in, minus 2 sine of that thing minus 3 cosine of that thing over x cubed. And the second one, y2 prime, is 2 cosine of that thing minus 3 sine of that thing, I'm outside my bars here, over x cubed. No, fourth. These down here are to the fourth power, aren't they? Yeah. Yuck! These are fourth powers here. Okay. Now, I hope I've got them right. So, here's how you do a determinant of a 2 by 2. Easy. Okay? You do the product of the down diagonal. I say easy. That's going to be 2 cosine squared of that thing minus 3 sine of that thing cosine of that thing minus the product of the up diagonals. That's going to be a minus, but this has a minus here, so I'm going to make that a plus. So both of these change to pluses now, and that will be 2 sine squared of that thing plus 3 sine of that thing cosine of that thing. I'm tired of saying of that thing. Okay. All right, and all this is divided by x to the 7th. Okay. Now, this minus 3 of that plus 3 of that goes to 0. Right? And then you got 2 times sine squared plus cosine squared. That's just 2. So you got 2 over x to the 7th. Right? Now, something to pay attention. Ooh, goodness gracious. Why wasn't I reading the book? But it still isn't bad. Okay? I want to point out to you, it says here, we've just done the unwieldy determinant, and it's not bad. But remember it said, somewhere here, I didn't write it down, I don't think. There's the differential equations. I didn't write this down on 0 to infinity. Okay, and notice that's a parentheses before the 0, which means 0 is not included. Thank you very much, because 0 couldn't be included for that. Now, why couldn't negative numbers be included? The log. That's in our original problem. It could possibly be included, and neither could 0, because, well, 0 couldn't for the log, because it executes in the denominator. So yeah, 0 is ruled out, but for any other thing, this is positive number raised to power, so be positive. Okay? Never 0. Wouldn't hurt if it was negative, that's fine, but it can't be negative, not for positive x's. And so that's always non-zero. That Wronskian is non-zero. That's all it takes. For the Wronskian to be non-zero for every x in the domain, then you've got it. They plugged in x equal 1. Isn't that?
That's very convenient.
Yeah. And if you plug in 1 for what we did, what do you get? 2. And that's what they got. So yeah, but you plug in any other number and you get, so ours is, we did the unwieldy part and it worked out fine.
But I didn't know how to do that, so I'm glad you did it.
Okay.
I've never seen that.
Okay. Let's do the simpler one just so you can get to see another one. When they plugged in 1, their determinant became 1, 0, negative 3, 2. Okay, and again, the determinant of that, and these bars mean determinant, is 2 minus 0. So that's equal to 2. Yeah. So that's how you do.
Like, say that 0 was a 1.
Okay. That would have been, if this had been the determinant, 1, 1, 1, minus 3, 2. Okay, that would be 2 minus a minus 3, which is plus 3. That would have been a 5. Yeah. Okay. All right. So, you don't have to figure out C1s and C2s and do all the things we did before for linear. All you have to do is do your determinants. Do your derivatives and set them up in a determinant and see what you get. Now, I haven't shown you how to do a bigger determinant. Let's see if they lead you to one. If not, I'll show you how to do bigger ones. Now, do I have room for that definition? Probably not. Let me go on and clean the page, okay? Oh, okay. Now, we got started closer to 320, wasn't it? So we'll go to 35, right? Yeah. Okay. I meant to say that at the beginning. All right. A set of n linearly independent solutions of a homogeneous linear nth order differential equations is given a special name. Okay? And here is the definition of that special name. Any set y1, y2, y3, up to and including y sub n of linearly independent, okay, solutions of the homogeneous linear nth order differential equation on an interval I is said to be, here's the special name, a fundamental set of solutions. Okay, fundamental set of solutions on the interval. Okay, now, here's the key pieces of this. If you have an nth order linear differential equation, blah, 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 okay, then you've got to have n solutions. Okay, you're going to have n solutions, okay, and potential solutions, okay. Now, if those n solutions are linearly independent, then it's a fundamental set of solutions for that differential equation on that end. If you didn't have n for an nth order, you don't have a fundamental set. They may be linearly independent, but it's not a fundamental set unless you have n for an nth order linear differential equation. Now, if you have n solutions for an nth order, okay, but they're not linearly independent, you don't have a fundamental set. They have to be linearly independent. So if you have n of these for an nth order and they all are linearly independent, Wronskian, okay, then you have a fundamental set. Does that mean it's the only one? Is it unique? No. No, you can have other functions that could form it, but any other function you put in, you'd have to take one out because you can't have more than n for an nth order. Okay, the next one you put in will then be linearly dependent on something, some of those others. Okay. Now, the basic question of whether a fundamental set of solutions exists for a linear equation is answered in the next theorem. So let's see if we can get it here. There exists a fundamental set of solutions for the homogeneous or homogeneous linear nth order differential equation on some interval I. There does exist a fundamental set of solutions for a homogeneous linear nth order differential equation on I. There does. There's got to be one. Okay? If it's a linear equation, there's got to be one. Analogous to the fact that any vector in 3 dimensions can be expressed as a linear combination of the linearly independent I, j, and k, similar if you have a fundamental set, then any other vector that is a solution is some linear combination of those. Okay? In other words, the n linearly independent solutions are the basic building blocks for your general solution. Okay. That leads to theorem 4.1.5, which I don't think I'm going to have room to write. So let me erase this and go here. Let those y's, y1, y2, y3, dot, 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 up to and including y sub n, be a fundamental set. I could have left the first part of that. I thought that of solutions of the homogeneous or homogeneous linear nth order differential equation on I of all the same we had there. Then the general solution another definition, general solution, okay, of the equation is y is equal to C1, Y1, plus C2, Y2, plus C3, Y3, plus dot, 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 plus C sub n, Y sub n. Where, yeah.
If we find any solution, any homogeneous linear solution,
Right.
then any set of constants will also be a solution.
Right.
Does that conflict with 4.14?
4.14. No, it's not going to be a fundamental set. Yeah. What this is saying, yeah, your general solution will be any linear combination of your fundamental set. Okay? Where these i's are 1 to n is the only thing I've left off. Or arbitrary constant. No, where ci, when I is equal to 1, 2, 3, dot, 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 up to and including n. Sorry. Or arbitrary constants. Okay. Now, yeah, we have infinite number of solutions, okay, as you see here, because these are all arbitrary constants. They can change to be anything. But these are some set with the same number of them like it, or your fundamental set, and the general solution can be made of any combination of those. And, yeah, but it might seem like, well, anything will be a solution. No, it won't, you know. It has to be combinations of those, that fundamental set. And these are just constants. I mean, it's like, if this vector and this vector define the plane, well, then you can make this vector longer, shorter, and this is longer, shorter. Any linear combination of those vectors will still define the same plane. So that's all these are doing, are scaling up and scaling down. Some of them could be going to 0, and yeah, all those things are possible. But that fundamental set, or one that's very similar to it, that is also a fundamental set, that's going to be the backbone for this. You've got to have n of them because you have n-order differential equations. And if you find those n of them that are linearly independent, that's a set. You can find another n that are linearly independent, that's another fundamental set. And then those same general things could be gotten from either sets or combination. They'll be just different constants. Okay. Ooh. That almost looked like 4.1.6. I was starting to turn the page. Yeah, let's do example 7. All right. Can I move on? Okay. Example 9 is finally going to do a 3 by 3 determinant. By the way, your determinants always are square matrices. 2 by 2, 3 by 3, 4 by 4, 7 by 7. Don't ever do a 7 by 7. Okay. All right.
I don't want to.
No. You wanted to do all those derivatives, I didn't. All right. Example 7. Bill said you did. Okay. All right. General solution of a homogeneous differential equation. Here's a function. y1 is equal to e to the 3x. y2 is equal to e to the minus 3x. These are both solutions to the homogeneous linear differential equation y double prime minus 5 minus 9y is equal to 0. Y double prime minus 9y equals 0. Now, these are really easy to show these are. Okay? Because y1 prime is what? 3e to the x. y1 double prime is this 3. Yeah, 9e to the 3x. y2 prime is equal to negative 3e to the negative 3x. And y2 double prime is 9e to the minus 3x. Okay, if you plug y1 in here, that would be 9e to the 3x minus 9 times e to the 3x. Obviously, that's 0. Okay, if you plug y2 in there, you get 9e to the minus 3x minus 9 times e to the minus 3x. That's obviously equals 0. So both of those are solutions without a doubt, right? All right. Now, whether they're linear independent or not, that's where the Wronskian comes into play. So we don't need the second derivative for the Wronskian. You know, it only goes up to n minus 1 derivatives. So let's get rid of that, okay? And I don't think we need this anymore either. But let's get rid of our commas and make this a determinant. That's your determinant. y1, y2, y1 prime, and y2 prime. Forget about the y's. Let's go on and get rid of those two. Okay. Could have brought my lines in further. Okay. All right. Let's do our determinant. The down diagonal will give us 3, or minus 3. What's e to the 3x times e to the minus 3x? 1, right? Because it's 3e to the 3x over e to the 3x. Yeah, the x1 goes to 0, and that's 1. So that's a minus 3, and then this is a, yeah, but it's minus because it's an up diagonal. Minus 3, that's equal to minus 6. That's not 0. All that's required is a Wronskian, not 0. Be any number in the world. 0.0073. You know, that would be fine. It's not 0. Okay. Therefore, you can conclude that y1 and y2 form a fundamental set of solutions because you have two of them. They're linearly independent. So therefore, your general solution would be y, I wish I hadn't erased everything now, y is equal to c1 e to the 3x plus c2 e to the minus 3x. That's your general solution. Got it done. Okay? On whatever interval you have. E's are good everywhere. All right. I think we can do example 8, can't we? Got it? Do you need it a little longer? Okay. Let's do example 8. Ooh! I just as soon not do example 8 because hyperbolic signs, I don't like them. But actually, I'm going to write down what a hyperbolic sign is. Y is equal to 4 times the hyperbolic sign of 3x minus 5 e to the minus 3x. Okay. Now, let's look very little good information on it. Let's see, is there an appendix somewhere here? Oh, here we go. Yeah. Yeah, I think I remember it too, but I wanted to show you where you can look it up. But since I'm not finding it real super quickly here, let's see if I find it in the index. That's not the index. Hyperbolic sign. I'll give it to you if I can't find it. Oh, they don't even have it back here. Let's just say, listen, cinch. People pronounce it that way. There's no C in it. Huh?
I don't see it in cinch.
Yeah. Did y'all used to call it cinch too?
Cinch or kosh.
Yeah, cinch or kosh. Kosh makes sense. Cinch. Okay. Here's what cinch is. Hyperbolic sign of x, I'm going to make it just x, so I'll go back and do that, is e to the x minus e to the minus x over 2, isn't it? Okay, that's it. And hyperbolic cosine is just with a plus sign in there. Okay? So why do you even bother? That's such an easy thing, easy to do, easy to differentiate, easy to integrate. Why mess up the picture with calling it a hyperbolic sign? It's just, okay, so this will be 4 times e to the 3x minus e to the minus 3x over 2 minus 5 e to the 3x, that's a minus 3x, and the 2 will go into 4 twice, so this will be 2e to the 3x minus 2e to the minus 3x minus 5e to the minus 3x, and that will be 2e to the 3x minus 7e to the minus 3x. Now, why didn't they just say y is equal to that rather than that mess up there? That's just as simple, in my mind, simpler. Because I don't have to remember the derivative of cinch. I don't have to, I can remember these. You do them all the time. So that's what your y is. Not going to mess with hyperbolics anymore. Okay, and it claims this function is a solution of the differential equation in example 7. That's the one we just did. Okay? Well, that's pretty obvious because the C1 is 2 and the C2 is negative 7. So, okay. So I think we just did the problem. Okay. Yeah, they have the hyperbolic there. And the thing is, we did it backwards. We showed what this was and then showed that is a solution to that differential equation because it's in the form where C1 is equal to 2 and C2 is equal to negative 7. So yeah, it was in that form. So we did that. All right, now the question is, can we get example 9 done? Here we have 3 functions. y1 is equal to e to the x. y2 is equal to e to the 2x. And y3, guess what, is equal to e to the 3x. Okay.
I'll give you the first and the second is y1.
You'll do what?
It's e to the x and e to the x.
Right. Okay, you're going to do those for me. Thank you so much. You're so kind. He's the kindest person I've ever seen. They claim that's satisfied the third order differential equation Okay. Y triple prime minus 6y double prime. Oh, one too many ticks there. Okay. Plus 11y prime minus 6y equals 0. It's a third order linear homogeneous, because it equals 0, differential equation. Okay? All right. So, they claim it satisfies, and like you said, it's pretty easy to show. Let's do it for the first one. That'd be e to the x. Okay, you just add your exponents, right? I mean, add your coefficients, because everything's going to be e to the x. Oh! All right. This will be plus 1 plus 11, that's plus 12 minus 12. That's going to be 0, right? Because e to the x, the first derivative is e to the x, second derivative is e to the x, third derivative is e to the x, all of them e to the x. So you can factor out e to the x, and what you have left is those coefficients. So that one's done. Okay, this one, that would be 8 for this one, right? E to the 2x is going to be everywhere, right? So you have a plus 8. So let's write it down. I'm doing that right, right? 2 times 2 times 2, yeah. That would be 8 minus 6 times 4 plus 11 times 2 minus 6, right? Okay? So this will be 8 minus 24 plus 22 minus 6. Yeah. That's 30 minus 30, right? Let's do it for the third one. Okay? That would be 27 minus 6 times 9 plus 11 times 3 minus 6, right? Okay? See what that gives us. 27 minus 54 plus 33 minus 6 minus 60 plus 60. Those are not too bad, were they? You got what we were doing? Because the functions stay the same, you know. Okay. So I love exponentials, okay? So let me erase those. So we're convinced all three of those are solutions. Now the only question is, are they linearly independent? And how do we do that? The Wronskian. Okay, what goes in the top row? E to the x, e to the 2x, e to the 3x. Okay? What's in the second row? E to the x, 2e to the x, 3e to the x. Now it goes in the third row. E to the x, 4e to the x. What's that? Oh, goodness, you got it. Yeah. Wait a minute. Yeah, this is 2x, 2x, 3x, and e to the 3x. Right? Okay. Now, obviously, well, nothing too obvious in it. Okay. Now, I showed you how to do it for a 2x2. A 3x3, you can't do that same thing. So here's what you do. It's a trick, and it only works for 3x3s. Repeat the first two rows. That's the first two columns. E to the x, e to the x, e to the x, e to the 2x, 2e to the 2x, 4e to the 2x. Okay? Yeah, possibly. Now you do the down diagonals here. And what do those multiply to? Well, the coefficient's 18, and when you multiply these together, that's 6x, e to the 6x, okay? Then we'll do that down diagonal. That would be 3e to the 6x. Okay? And this down diagonal. Plus 4e to the 6x. Now we're going to subtract our up diagonals. That would be a minus 2, right? E to the 6x. This will be a minus 12 e to the 6x. I left off my x. And this will be a minus 9 e to the 6x. Okay, let's see what those add to. These add to 7 and 18 is 25, right? And these add to 21 minus 2 is minus 23. 25 is not equal to 23. Not, all it matters, not equal to 0. Oh, and by the way, e to the anything will never equal 0. Ever. Okay? So, yep, not equal to 0. That's all you need. It doesn't matter what it is. They got it. 2e to the 6x, which is what we got. 2e to the 6x, and that is not equal to 0. Can never be equal to 0. 2 is not equal to 0. e to the 6x is never equal to 0. So therefore, and this is good everywhere, every value whatsoever. And so you get y is equal to c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. And it doesn't matter which one you put 1, 2, and 3. You could have put c1 e to the 3x plus c2 e to the x plus c3 e to the, I mean, those are just arbitrary constants. They're just not necessarily the same constant. They could be, but they don't have to be. All right. And because the Wronskian is not 0, we finished 4.1.2. Okay. This is one long section, isn't it? Okay, I think no. We got some time, don't we? Or do we?
2 minutes.
Huh?
2.
2 minutes? Is that all?
Yes.
Oh, wow. Okay.
One quick question.
Yeah.
What that Wronskian is used, or is that just a fundamental operation like we just use determinants in regular algebra or regular?
Yeah, linear algebra is used all over the place. Not all over the place, it's used a lot. Yeah.
There's nothing specific except it's just an operation by
It's
itself.
Yeah.
Just if
Right.
you call upon it, then you can do it.
Right. Yeah. And in the 2 minutes we got left, what if you had a 4x4? Okay. I'm not going to do a 4x4, but I say, what if you had one?
I would say you
Huh?
make a subdivision, say,
Okay.
expand it by a row.
That's exactly it. So let's say we had A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, A41, A42, A43, and A44. If you're doing that determinant, pick a row or pick a column. It doesn't matter which. Well, it does matter which. Pick the one with the most zeros in it. Okay? That's not going to make your life easy. Okay? So pick one. I don't care which one. Any one. Which one? Column or row?
First row, first column.
No, just pick one. A row or a column.
First column.
First column. This one right here. Is that the one you meant?
Yes.
Okay. What we'll do then, its determinant is A11. Now, I say A11, I'm going to tell you a couple things. First, we have signs for each of these positions. And they're really simple. Plus, minus, 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 plus, minus. Or plus, minus, plus, minus. They're all the same. These are always going to be plus. These are always going to be plus. These, Yeah. Yeah. No, okay, I said it wrong. Yeah, in this case, that's going to be the case. In other words, here's one way to look at it. If the subscripts are even, they're pluses. If they're odd, they're negatives. So it's going to form a patchwork. Always alternate. No matter which direction you go. Just don't go diagonal. Okay? Go up or down, left, right, up or down. And they always change sides, plus, minus, plus. Okay. So this is a positive position, so it's going to be A1 times the determinant made when you wipe out the first row, first column. There's a 3 by 3. And you know how to do a 3 by 3. Okay, so do it. Okay, then you pick this one. So I'm just going to do that. That's going to be the 3 by 3. So then we go to the next one, which is A21. Okay, so that would be a minus A21 because those subscripts are odd. They add up odd, times, wipe out that row and that column. You already wiped out the row column, you chose that. And then you put this one in. A12, A13, A1, I can't write it, 14, A32, everything that's left that you didn't wipe out. Okay? Then, once you do, and you know how to do that 3 by 3, expanding it and going. Okay? Then see, these can get really long and obnoxious, but they are doable. Okay? Wipe out that one and go to the third one. Okay? And wipe out that row. Now, this is a positive position, right? So it's going to be plus A31, because those add to be positive, times this one that's left over. A12, A13, blah, blah, blah. You just skip the A32s. A22 goes to A42. Blah, blah, blah. And you know how to do those. And then you go to the next one, A41, be a minus A41 times what's left over when you wipe that out. Okay? Now, so you see, if you pick the row or column with the most zeros, then these are all zeros. And they make it really easy to do. But if you have 5 by 5, you go down to 4 by 4s, then you go down to 3 by 3, and then you know how to do a 3 by 3. So you always do it this way. Pick any row, any column, and then proceed.
But you can make you can go out to a 2 by 2 if you want to, right?
Yes, you can go down to a 2 by 2 if you want to, and then you got it done. Yeah. But the 3 by 3s are easier than going to all those 2. Well, depends on how many zeros you got. Okay. So that's how you do the big ones. I'll try not to give you too many bigger than 7 by 7. No, I'm just kidding. Because you see, this will take a while to do.
I will mess up a 7 by 7.
Yeah, no, I will too. All right. I think we did now use up all our time, didn't we? All right. So Corey didn't make it in today, and either class. We'll start with 4.1.3 next time. Homework exercise. Oh, I almost forgot. Y'all should remind me of these things. You could do any of the odds that are in the back of the book, 1 through either 1 or 3. Any of the odds, either 5 or 7, 9, and 11. If they're in the back of the book, do them. 13. In 4.1.2, do any of the odds 15 through 21, and any of the odds 23 to 29. Stop there. We'll pick up non-homogeneous or homogeneous equations next time. And I think we'll finish those pretty quickly because that's only a page and a half, 2 examples. So I think we'll be able to do that. Because this is the rough sledding right now. The non-homogeneous, it'll present more challenges later, but not right now. They'll be pretty easy right now. All right, to erase, or are you still getting this?
I'm writing it, but I think I'm done.
Okay.
And you're going to be close. All right.
Now, when you take a course in linear algebra, they talk about minors and cofactors and all these things. This incorporates all that. Basically, what a minor is what's left over when you take out the row and column. You're using that thing. So that's the minor. The cofactors just is what pluses or minuses the minors. Okay, which is what we did here. I just showed you how to do that with the right, left, up, and down. Okay. Just assign a sign to each one. Basically, is about whether so you usually don't have A32s there. You have numbers there. Yeah. So to keep up with whether that's even or odd, you have to do it's just plus, minus, plus, minus, plus, minus, plus. Yeah. It's real easy to do. All right. All right,